I hope now you appreciate the research in this space, how to design protocols. Anyway, so the spanning tree algorithm is a dynamic distributed algorithm, and this is how it is done in practice. At the beginning, each bridge thinks itself as root because it has no idea of what the IDs of the other bridges are. And then it is going to generate this configuration messages and send it out on all its ports. Now, what is this configuration message? It's basically this 3 tuple where X is the ID of the bridge that is generating this message. D is the distance to Y, which is the root bridge, what it considers to be the root bridge. Now, each bridge is going to receive such configuration messages from its neighbors, and based on that, it is going to store the best configuration. What do I mean by best configuration? Any configuration is better than the one that is stored if it identifies a smaller root ID, or the same root ID but it is at a shorter distance to the root, or same root ID and distance but a smaller sending bridge ID. These are the same rules that we discussed before. A few other subtle points. A bridge stops generating configuration messages once it decides that it is not the root, but it still forwards configuration messages after incrementing distance, but it is not generating configuration messages by itself. Not only that, a bridge stops sending configuration messages on a port if it is not the designated bridge for that port. Finally, in the end, only the root node periodically generates configuration messages which are sent to all the other bridges in the extended LAN. Nothing like an example, so let's focus on this topology, specifically at bridge 4. At the beginning, bridge 4 views itself as the root, so it is going to generate this configuration message and it is going to send it out on all the interfaces. So this configuration is saying I am the root, I am at a distance 0 to myself. Other bridges are also going to generate similar configuration messages and are exchanging them with each other. Let's suppose that B2 already received one such configuration message from B1 and thereby updated that B1 is the root and it is at a distance of 1 to B1. Now this B2 has sent this particular configuration message on F. The question is, what does B4 do when it receives this configuration message? So B4 immediately knows that it is not the root because B1 has the smaller ID, so it accepts B1 as the root, and since it can reach B1 via B2, it will designate this B4F as the root port. Based on this message, it will also conclude that it is not the designated bridge for F because this message was received on F, which means F is interconnected to B2, thereby it is better for F packets to go via B2. In other words, B2 is the designated bridge for F, thereby it is not going to act as the designated bridge for it. So what about for LAN segment E? Who does B4 think is the designated bridge for E? It considers itself as the designated bridge because it did not hear any other configuration messages from other bridges. Similarly, for C also, it views itself as the designated bridge. B4 will stop generating configuration messages because it is not the root anymore, but it is still going to forward the configuration message. So the question is, what configuration message is it going to forward? And secondly, on what ports is this configuration message going to be forwarded? So the message it forwards is this, where it says I am B4, I am at a distance 2 to B1, and it is only going to send it out on E and C because it is not the designated bridge for F. So this is, since it is the designated bridge for E and C, it is going to send it only on E and C. But note that all its ports are active because this is the root port and these are the designated ports. We are still focusing on B4. Now suppose B4 were to receive this configuration message on C. As far as who the root bridge is, this doesn't change. B1 is still the root bridge, and the root port also doesn't change because B2 has a smaller ID than B3. As far as LAN segment F is considered, B2 is still the designated bridge at distance 1. As far as LAN segment E is concerned, it did not hear any configuration messages on that. So B4 is still the designated bridge for LAN segment E. What about for LAN segment C? Now C, it is going to update that the designated bridge for C is B3 because it received this configuration message on C and it knows that B3 is closer to B1 than itself. Thereby, it will conclude that B3 is the designated bridge for C. So in response to this configuration message, what does it forward? And on what ports? Right, it is now going to forward this particular configuration message only on E. This is not the designated bridge for F or C. It's only the designated bridge for E. It should be obvious by now that only the ports, this is the root port and this is the designated port, only these both are active. It has disabled this particular port. B4 should not have received this configuration message B5 on E at this time because it had already sent this particular message on E. B5, when it received this configuration message from B4, would have concluded that B4 is the designated bridge for E, and thereby this would have disabled this particular port. So this message would not have come to B4. So B4 will continue to be the designated bridge for E. I hope this explains how the configuration messages are exchanged and how bridges act on the configuration messages. The end result of all this is a spanning tree is imposed by disabling the required ports that introduce loops into the topology. Great, but what if a bridge failed? So look at the spanning tree. Suppose bridge 3 were to fail. Now you have a disjoint graph. While in reality there is a path that interconnects C to B4, but right now it is disabled. So you need to come up with a new spanning tree that is going to interconnect the different LAN segments. How is this done? So whenever a bridge fails, what happens is the downstream nodes stop receiving the configuration messages that are periodically sent by the root. In which case these downstream bridges are going to time out when they don't see such configuration messages and they are going to declare themselves as root. Now when this happens, the spanning tree algorithm will again kick in and you're going to elect new designated bridges. We will work out an example as part of the quiz to figure this out. So bridges are cool in that they extend the LANs, but there are some fundamental limitations with using bridges. There are quite a few. Think of at least two. One biggest limitation of bridges is that this solution is not scalable, and there are many reasons for this. One is the use of flat addressing. In other words, there is no hierarchy that can be imposed on top of the media access control addresses that Ethernet employs. What do you mean by this? Now suppose there are 10,000 hosts as part of your extended LAN, then your forwarding table can potentially contain 10,000 entries, and whenever a packet comes with a destination, you have to look up one after the other each of these entries to figure out which port to send this particular frame on. So for 10,000 hosts, the lookup may not take that much time, but if we want to scale the network to millions of hosts, this lookup itself can take up considerable time. Thereby, it is not feasible to use bridging when you want to interconnect millions of hosts. The learning that is done as part of bridges, I had already mentioned, is an optimization. In case you don't have a destination address as part of your forwarding table, you are just going to send this frame out on all your outgoing ports. This will basically result in flooding of the frame in the entire extended LAN, which is not desirable. You will be amazed by the number of broadcast frames that are sent on link. Just do a TCP dump to figure it out. Since there are many broadcast frames resulting from protocols like ARP, DHCP, we didn't cover this, we will do it later. Such broadcast frames are again flooded everywhere. Imagine all the hosts in India interconnected through extended LAN. So someone who is sending an ARP packet, a broadcast packet in IIT Delhi, you're going to receive it here in IIT Mumbai, and it doesn't even make sense to receive it here. And majority of the link bandwidth will just be consumed in broadcasting such frames, leading to very poor utilization. There is yet another limitation to bridges. The spanning tree algorithm itself can lead to inefficient paths, and this also prevents load balancing. What do I mean by this? Suppose a host in LAN segment E wants to send a packet to a host in LAN segment B. If you see this figure, they are just interconnected via one bridge. But because you have imposed the spanning tree and removed that particular port, this packet essentially has to travel all the way up and come back down. So this is not very efficient. Not only that, there are multiple paths between any two Ethernet segments. Because you are imposing a tree, you are not relying on the multiple paths. In fact, that is what causes loops. But at the same time, if you want to do load balancing, it will not permit you to do load balancing. Yet another problem with extended LANs. The problem again is that you cannot handle heterogeneity. So if you look at a bridge, it's going to look at the source address to determine how to forward, and unless the networks it is interconnecting have the same address format, it cannot act on the source address. So when you're using Ethernet switches, typically these are used to connect Ethernet LANs alone. All in all, there are many limitations of using bridges to extend LANs. So here is a summary of what we have learned. So extended LANs can build relatively big networks, but in such topologies, loops are unavoidable, maybe due to misconfiguration or purposefully introduced for fault tolerance purposes. Now these loops can be avoided by imposing a tree on the network graph, and we saw that all this operation is plug and play, no changes to the host, no manual configuration of the bridges. But still quite a few limitations when using bridges. So up ahead, we will look at network layer switching to overcome these limitations. Hooray, we are done with link layer now. I will end this video with this cute little algorithm by Radia Perlman. She is the person who designed the spanning tree protocol.